This is the review packet for the Fall 2014 final exam. Question number 1. The graph above represents the motion of a car. Based on the graph, describe the motion of the car. So, if the car is moving here, this is position versus time. So, the slope of this line is the velocity. So we just have to calculate the slope of the line, and the slope of that line is the velocity. You can see that it's moving at constant velocity because the slope isn't changing. So we could say constant velocity. We could also calculate the acceleration if we wanted to, or the velocity if we wanted to, by doing rise over run. Question number 2 says the graph represents a car driving on a straight level highway. Which of the following is the velocity of the car at 2 seconds and 4 seconds? So we have to take a look at the velocity at 2 seconds. Well, at 2 seconds and at 4 seconds, now this is a position versus time graph, not a velocity versus time graph. So we can't just read it off the thing. It's not 10 and 20. Those are its positions. We need the slope. The slope is the same, and the rise is, so the slope is equal to the rise over run. So it's equal to 20 meters over 4 seconds. So that's equal to 5 meters per second. And that's the same either at 2 seconds or at 4 seconds. Okay, question number 3 says, what is the velocity of the object shown in the graph at left at t equals 5 seconds, and what's the initial velocity? So what we need to do first is we need to go at t equals 5 seconds, so we go straight up there, and then we read straight across on the graph, and you can see that it says 15, and the units are meters per second. So the first part of this is 15 meters per second. The next part, what is the initial velocity? So the initial velocity is the starting velocity. So that's at t equals 0. Well, where does this intersect the line? It intersects the line at 10 meters per second at t equals 0. So that's the initial velocity. Number 4, list whether the examples below represent constant velocity or acceleration. Well, without changing velocity, that should be obvious. That's constant velocity. A mass thrown upward vertically at 10 meters per second, well, that's the initial velocity, but obviously gravity is having an effect on there, so gravity is always acting, so this is acceleration. A jogger runs along a 50 meters along a straight track at constant speed. Well, constant speed, that pretty much tells you constant velocity. An elevator moves vertically upward past 4 floors at 0 acceleration. Well, obviously, if there's no acceleration going on, then that's also constant velocity. The last one says a rock comes loose and rolls down a hill. Well, if it's rolling down a hill, it's subject to gravity, which means acceleration. So these 3 are constant velocity, and these 2 guys right there are operating under acceleration. Consider the velocity versus time graph for your car. That's this car right here, shown at left. How would you describe the motion of the car? Well, the first thing we want to do is we want to look and see what's going on here. And if you look, you can see that on the velocity versus time graph, it's a perfectly straight line. The straight line is acceleration on a velocity versus time graph. So it is doing some sort of acceleration. Is this slope positive or negative? Well, it goes downhill, so it's negative acceleration. If this is a car and we make the assumption that it's moving forward, then at the beginning up here it's positive, and down here it's negative. So the car is going straight, and then it slows down to a stop, and then it begins speeding up going the other way. Describe the velocity at these 3 times. Well, at the beginning, it's a high positive velocity, and that is a positive. then it slows down, slows down, slows down. Then at t equals 1 second, well, it's 0 or stopped. And then as it continues on down at 2 seconds, it is high negative velocity, negative right there. So this is almost just like throwing a ball into the air. It starts off moving fast up at the top, up here, and then it slows down to 0 right here in the middle, and then speeds up on its way down. So there's obviously some acceleration going on there. Next question, look at the displacement versus time graph at the left and describe the motion of each graph. All right, in this first graph, it's accelerating because it starts off shallow and it ends up steep. In this graph, in a position versus time or displacement versus time graph, a straight line indicates constant velocity. So this is constant velocity negative, going towards the origin or towards the starting point. In this case, we start off very steep and we end up very, very shallow. So we're slowing down as we head towards the origin. So we're slowing down in the negative direction. We're basically going backwards fast and coming to a stop. In this question, in this one right here, we're slowing down because we start off steep and we end up shallow. So we're slowing down in the positive direction. And then here we have a straight diagonal line, so that is constant velocity in the positive direction. Here, a runner travels at 90 meters at a steady pace of 6 meters per second. So 90 meters at 6. What is the time, is what they're asking. Well, velocity is equal to distance divided by time. So time is equal to distance divided by velocity. So I'm going to take this down here. 90 meters divided by the velocity of 6 meters per second. The meters cancel and seconds goes back up on top, and 90 divided by 6 is 15 seconds. Number 10, right here, a hockey player gliding over the ice at a speed of 2 meters per second accelerates at 2.5 meters per second squared for 3 seconds. His final speed is what? Well, we're going to use this equation. The final velocity is equal to the initial velocity plus a times t. So the final velocity is equal to his initial velocity, 2 meters per second, plus the acceleration, which is 2.5 meters per second squared times 3 seconds. So that's equal to 2 meters per second plus 2.5 times 3. That is 6.5, right? Or 7.5, sorry. 7.5 meters per second. And so together that's 9.5 meters per second. Next one, number 11, a car travels 15 kilometers due north, so that's 15 kilometers, and then travels 9 kilometers west. What is the approximate magnitude of the displacement of a helicopter that flies in a straight line? So flying in a straight line, of course, we go right here. So we shortcut, and this is just the hypotenuse of a triangle. If you remember Pythagorean theorem, c squared is equal to a squared plus b squared. So it's equal to 9 squared plus 15 squared. So that's equal to 81 plus 225. So that's equal to 306. So c squared is equal to 306. That means that c is equal to the square root of 306, which is about 17.5. And of course these units are kilometers. And that's just the hypotenuse of a right triangle. Number 12, a baseball was thrown with an initial horizontal velocity of 14 meters per second. It remained in the air for 2 seconds. Which quantities are constant and which change while it's moving? Well, the ball was thrown in this direction with a horizontal velocity of 14 meters per second. This is the ball. So what actually happened to the ball? The ball took a parabolic path like that and eventually hit the ground. So what's changing? Is acceleration changing? The answer to this one is no. This is constant. Because acceleration is caused by what? It's caused by gravity. And it doesn't change no matter what. Displacement, well, that's the distance from the starting point here to the ending point over here. And obviously the displacement is changing, so that's changing. Its position likewise is changing. What about the velocity? Well, there's actually two velocities. One velocity is the horizontal velocity, which was the 14 meters per second. That's not changing. But what about the vertical velocity? And that's Vy right here. This is Vx. Vx doesn't change. Vy does. Why? Because it's affected by gravity. So the velocity, which is the combination of those two vectors, roughly in that direction, is changing. So all of these change except for acceleration, which remains constant. Number 13, an airplane is cruising at constant velocity and height above the ground. Thrust is the force that pushes the plane to the right, and drag is the wind resistance pushing to the left. Draw a free body diagram that represents the four forces on the airplane. So I'm going to start with a little dot right here, and I'm going to draw these two forces, and this will be the force of gravity or the force of weight. This right here represents the force of lift. That's what the L stands for, is lift. The force right here is the force of thrust. And the force here is the force of drag. Notice the free body diagram that I drew. In this free body diagram, these two exactly cancel each other, and these two exactly cancel each other. Why? Because it is moving at constant velocity. If any of these were larger, then that would mean that it was not at constant velocity and there was some acceleration going on. Draw a free body diagram that represents the forces acting on a raindrop falling vertically at constant velocity. Okay, so here is my little raindrop. Not a great drawing. Okay, are there any forces going side to side? And the answer to that is no. So we don't have any. We're not talking about wind. So what we need is a dot and a force going up and a force going down. It's easier to draw it over here. Here's my dot. Force going up, force going down. So we have the force of gravity or the force of weight, and then we have the force of drag, and this is air resistance. When it's moving at constant velocity for a falling object, that would be its terminal velocity as well. That's the velocity where the force of gravity and the force of the air resistance are the same. Number 15, the illustration at right shows the forces on an automobile as it moves. If the applied force is greater than the drag force, describe the motion of the car. So in this case, the applied force is bigger than the drag force.
Okay, you can lock.
That means that the net force is in this direction, which means that there is acceleration in this direction. So the acceleration is in this direction. If the drag force is greater than the applied force is this way, and the drag force is greater, then the car would be slowing down, assuming that it's already moving. Notice that the normal force and the gravitational force are the same, which means they cancel each other out, so there's no net force up or down.